Well, okay, good morning. Hope you had a nice weekend. I guess the first real fall weekend here with rain and all sorts of things that we are not used to yet. Well, here we will talk about something a little bit new about inductors. Inductors are kind of the complement or in a way the complement or the dual to capacitors. And I guess you already read about inductors in the book, and you sort of read the run-of-the-mill stuff. The symbol you're probably familiar with now. Today we will more try to get a feel for what an inductor really does, and we will also compare it a little bit more to the capacitor. The capacitor, we said, it stores flux. It stores charge, right? And it's like a bucket where we can put charge in, and then later, if we want to use it, we can get it from there, so we can treat the capacitor, for example, like a battery. An inductor stores flux, and one way to think about it, it's not exactly true because electrons have, of course, very small mass. But if you think about the water going around in a circle or so, if you had water in a pipe or so, then, of course, that water, when it's flowing really fast, even if you turn the water off, so the water shoots way out, right? And that's the same thing if you have current going really strong in a wire. You can't just turn it off, right? It keeps going. And we will look at and in an inductor, that's really happening. That phenomenon is really strongly present in an inductor, and we'll see what that really does for circuits. Okay, so here are a bunch of inductors, how they look like. You can check those out on the website. Here the mass of inductors. I mentioned they're kind of like a dual to capacitors. So if you remember this equation, the reason I remember it is charge is proportional to voltage. That's what I remember, and then I just take the derivative if we want to get the differential equation. You can use whatever way to remember this, but you need to remember that. And then I also remember that the inductor is just a dual. So instead of putting current here, I put voltage here, and here I put the current. Okay, and then I have these two equations. These you need to know. 1/2 CV squared. You probably remember this already. That's the energy stored in the capacitor, and 1/2 Li squared. Again, we go from voltage to current. We go to the dual. That's the energy that's stored in the inductor. Now, let's try to get a little bit insight, or let's put a little bit of insight into this equation. Well, first at the top, we'll look at the capacitor that we are quite familiar with, so that shouldn't be too hard. And then we'll do the same thing again for the inductor. So if you look at the circuit at the top, you have this switch there. The switch can go from the left side to the right side. So if it's on the left side, then really the resistor is totally disconnected. So we have, well, let me draw this here. What we have is a voltage source and the capacitor simply connected to that voltage source, right? That's when the switch is in the left-hand position. Okay, so let's say here the switch left, and here it's on the right side. Okay, so if the switch is in the left side position, what is the voltage across the capacitor going to be if we wait for a long time? Okay, it's just going to be V1, right? So the voltage is going to be V1, and what's the current going to be? The current is going to be 0. Okay, and now we throw the switch onto the other position, so now we get the capacitor connected to the resistor, and the voltage source is removed. What's going to happen? Okay, the voltage will initially just will stay the same, right? Across the capacitor, we cannot change the voltage instantaneously. What would we have to do if we want to get a voltage step on a capacitor? If we want to, in a infinitesimally short instance, we wanted to change the voltage across the capacitor, what would we need? An infinite current flowing, right? Because the voltage is because the current is proportional to dV dt, and dV dt, of course, would be infinite, so the current would have to be infinite also. All right, so initially it's just going to be the same, but then, of course, afterwards, as you said, it's going to decrease, and it will ultimately become zero, right, when the capacitor is completely discharged. Okay? And so, so there are three values that you easily can determine in this curve. You can determine the value here before the switch is thrown to the right-hand position. You can determine the value just after the switch is thrown. Okay? It's the same. And you can determine the value after waiting for a very long time. Such boundary values, very often you can determine very, very easily. You don't need to solve or write or whatever any differential equations. But if you can determine these values, typically you can draw these characteristics rather quickly, and you understand what the circuit's doing. So very often, that's kind of the most important thing that you will have to be able to do when you have circuits with capacitors, inductors. And then afterwards, of course, you can start writing differential equations and solve them and so on. You get the exact shapes in between. Okay, so this is what happened to the voltage. What about the current? You already told me the current was initially zero. What is the current? What is the value of the current going to be just when I throw the switch to the right-hand position? Actually, I would like to know the value of the current. Anybody could figure that out. Exactly. It's just going to be equal to, yeah, exactly. It's V1 over R1, and I guess it's true that because the current runs this way, it's actually going to be negative. Okay? And then so the current does jump for the capacitor. The capacitor has absolutely no problem in suddenly delivering a huge burst of current. And I already told you that, or we talked about that, right? That's a big advantage of capacitors, that if you suddenly need a pulse of current, no problem, the capacitor can do that. A battery may have difficulty, but the capacitor can do that. And then, of course, the current is not going to flow indefinitely. It's going to decay, something like this. Okay, so that's what's happening for the capacitor, I guess. Let me write that here. Capacitor. Now we're going to use a different color, inductor. Okay, so same thing. We have this time we have a current source, and we have an inductor connected to that current source, and the current has a value I1. What's the voltage across the inductor if we wait for a long time? Okay. Why is it going to be zero? Yeah, exactly. That's the differential equation for the inductor. If they wait for a very long time, well, the current is not changing. Well, of course, the current's not changing. The current's actually fixed. It's I1. The IDT is zero. Consequently, the voltage across our inductor must be zero. Okay, so we can put that into our diagram here. Then,
why would the current ever change at all? Because there's no resistor, and all we have is just the ideal current source.
That's right.
So why do you keep saying after a long time?
Yeah, in this case, yeah, it's well. I guess the way I say that, the reason I say that is, of course, when you put this together, initially you turn this on, there is going to be some resistance here, and then it's going to go there. But it's true, I totally ignored the fact that how do we get to the position where the current I1 is flowing through through the inductor? Okay, that's why. I guess I could have added the resistor here and could have said that at sometime minus or sometimes zero, you turn on this current, and then what's happening, right? And then at some later time you switch. Okay. But I made the example here simple, so that's not the. Still the switch in the left-hand position. What's the current? Well, the current's very easy, right? The current is I1, of course. Okay. So now Now we throw the switch, and so what we have here now is here a resistor, and this guy is gone. Okay? So we have a resistor in parallel with this inductor. This is doing its thing. Somehow it's playing a video game here. It's very interesting. So we throw the switch into the right-hand position. Let's ask ourselves first, but what's going to happen to the current? It will somehow have to change. Yeah, you're right. The current will have to decay, but just immediately after we flip the switch, it's actually going to be the same, right? Because again, if there was a step in current, we would get infinite voltage. So it's going to look something like. Ultimately, it's of course going to decay, but initially it's going to look like. What about the voltage? Okay, so the voltage is going to be, well, whatever that current, I1, or here we have I1, right? And that's flowing through the resistor, and of course that produces a voltage R1, I1, okay, whatever that value is, and then it also will decay, okay? So that's what's happening with the inductor. Notice also that if you make the value of that resistor large, what's going to happen? The voltage can get really, really large, right? So we will use that later on, that we actually can use inductors to generate very high voltages if we want to. All right, so here I summarized all of this stuff, capacitors versus inductors. So let's just quickly read through this. Capacitors, they resist change in voltage, right? The voltage at least in a blink of a second stays the same, then afterwards it can decay or increase as we have current flowing in or out of the capacitor. DC-wise, they're open circuits. That means that for a very long time, if the voltage doesn't change anymore across the capacitor, so then the current's going to be zero. Well, if the current is zero, that circuit is a open circuit, right? Okay, so then we can use them to store a voltage. And we've seen that, so that makes perfect sense. Sometimes a little bit harder to understand these, but if we put them in context and compare them to what's going on for the capacitor, then it's actually usually a little bit easier to understand. So much like capacitors, they resist change of voltage, inductors, they also resist change of current. So whenever we switch or so, the current just after having flipped the switches is going to be the same. Remember that, okay? And of course, if you prefer, you can look at the differential equation. The differential equation tells you all of this stuff. Here we just interpreted them. DC-wise, inductors are short circuits. If we wait for a very long time, the current doesn't change anymore, then the voltage across the inductor is going to be zero. Okay? Well, if the voltage is zero, regardless of the current flowing, we have a short circuit. Okay? So it acts like a short circuit. Only DC-wise. DC means that we wait for a very long time and nothing's changing anymore. Obviously, when we make changes, that's not true. There can be very well a voltage across our inductor. It's not a short circuit. Then we could use inductors as a current memory. And what you would do is you would somehow use this kind of a circuit here on the left-hand side to set up a current flowing in the inductor. Then you would make this resistor actually zero, and the current would flow. You throw the switch into the right-hand side, the current would flow how long? Forever, right? There's no dissipation, so it would flow forever. In practice, it's very hard to do because in practice, you make these inductors out of wire. Well, the wire has resistance, so you really have this element there, whether you want it or not, and consequently, the energy is going to dissipate. Okay. All right, so now we have a pretty good feel for what these elements do. Now let's try to understand what they do in our circuits. Yes? Why would you want to remember? Well, in principle, actually I forgot to say that. Good question. Capacitors can store voltage. Well, how do you think DRAM, dynamic RAM, right? You know it. You know that. How do you expect that it works? That's exactly that. It's a sea of capacitors. If you have 1 gigabit DRAM, it's really, you have 1 billion capacitors, and they each store a voltage. That's it. Okay? And what you really do is you write a voltage onto a capacitor through a switch, and then later you go and read it out, and and you use that to determine whether it's a 1 or a 0. That's it. Okay? Now, obviously, you could do exactly the same thing with currents also, and you could imprint the current onto an inductor, and later you could go and read it out. You could make a memory that way. Nobody does it. Why? Well, because the capacitor is pretty easy. I mean, making a 1 gigabit DRAM isn't exactly easy, but conceptually it's quite easy. Whereas in practice, this is conceptually also easy, but making these good inductors or so and make them small and so it's totally hopeless. Nobody has figured out how to do that. That's why memories, they actually use this, but I've never seen one that uses this. The best I've seen once was at the particle accelerator in CERN in Geneva, and there they have big coils, and they actually were maybe cooled or superconducting, I don't remember. But they were not really storing current, but they were storing a field, and the field was there in order to accelerate their particles. Okay, so inductors find relatively less use simply because they're harder to make and more expensive. But that doesn't mean that they don't exist, and in fact, in many places inductors exist where we don't even want them. And let's look at the case like that first. So first of all, I've given you an equation for a parallel plate capacitor. And it's pretty straightforward and easy. Turns out that the same thing for an inductor is a little bit more complicated. But if you have a torus like that, imagine that was a wire that had a diameter A, and the radius of that loop is R. Then you find a relatively simple equation that tells you what is the inductance of this thing. Okay? So the inductance is given by this equation. I can plug in, and I find for R, that's actually 10 centimeters, and A, 1 millimeter, I find that I have like 500 nanohenry of inductance. Okay. So now, why does this matter? Well, let's look at this situation. Let's say we have a power supply, right, and then we have our electronic circuit. Of course, we have to somehow connect them together, and let's use wires like that. These wires, sure, you don't really quite make a loop with them, but it sort of looks like a loop. Huh? So really what you have is you have the power supply on the left-hand side, and then on the right side, you have the electronic circuit. In between, you have actually an inductor. It's really just wires that you put there, but these wires, they act like an inductor. And their value is a few hundred nanohenries. Okay? So the model would be that we have our power supply, some kind of a source, right? Then the wires, they're an inductor, and the load is probably some kind of resistance or so, right? That's really the circuit that we've built. This is also a good example that normally we say, hey, you know, wires, they're ideal, they're just zero voltage across no matter what current. Well, that's sometimes true, sometimes that's not a good model. Well, when it's not a good model, then we can replace our wire with something that's a little bit more sophisticated. Okay, so that's the model that's what we actually built. We didn't want to put an inductor there. Actually, we didn't order an inductor. Just by the mere fact of putting the wires there, well, gives us a little bit of inductance. Not very much, just a few hundred nanohenries. But what is it going to do that? What is it going to do? Well, here is a circuit where we can investigate this a little bit. If you look at this, the part on the left-hand side without the switch or with the switch open, well, that's just the circuit that we determined before that we actually built. We have some inductance, we have some resistance. If you can, wake up, because it's going to be a lot harder to understand afterwards from the notes. I guess he's gone. Okay, so we have this resistance here, and that's our load. Now, very often what happens in circuits is that the current that they draw is not constant. It periodically gets higher. For example, this week in the laboratory, you're building that 555 timer, that synthesizer. If you think about it, the synthesizer, it sort of runs, but then in every clock period, once in a cycle, it pushes basically an impulse of current into the speaker so that it makes some sound. Okay? So really the current from that 555 timer, for example, is going to look something like this. There is this is the current, and this is time. So there's a certain minimum amount of current that's used all the time, but then at the cycle, it's using a lot more current. Okay? So the real power or the real current draw from that 555 timer looks something like this. It's not very much most of the time, but then pulses of really large current. Digital circuits also operate like that, right? They operate on a clock. Whenever the new clock phase hits, then they draw a lot of current. Well, we can model that by having here a relatively large resistor that models the continuous current that's flowing. And then we have an additional smaller resistor here that models the fact that that we actually get much larger current flowing, and that switch here just turned on and off according to how our circuit actually draws current. Okay. So now let's try to understand what's happening with the current here and the voltage. So what is the let's stay first on the left-hand side here. So the switch is open on these two graphs. What's going to happen to the current in the again, the switch is open. What's going to happen to the current? Yeah, it's going to somehow, from wherever it was, it's going to increase or decrease or whatever. It's going to achieve ultimately the value Vs over R1, right? Because ultimately, if we wait for a very long time, what's going to happen to the inductor? It becomes a short circuit, right? So the inductor becomes a short circuit. Well, if the inductor is a short circuit, well, then this circuit really looks just like a resistor or one slapped across that voltage source Vs in parallel or in series with it, and consequently the current's going to be Vs over R1. All right, so that's the current going to be, and then the voltage, well, the voltage also is going to be, initially we may have some voltage drop across the inductor, so it may take some time to get up to that value, but ultimately the voltage V2 is going to be just equal to Vs the source. Again, because the inductor behaves like a short circuit. Okay, so now we flip this switch. Now let's imagine first that we flip the switch and then we wait for a very, very long time. What's going to happen? What's going to happen then? What's the new circuit? What does the new circuit look like now? Yeah, but what value is the new resistor actually? Exactly, right? It's just a parallel combination of these two resistors. Really exactly the same thing as we had before. And the inductor, what does it happen if we wait for a long time? Becomes like a short circuit. Okay, so it's exactly the same kind of argument as we made before. The voltage now is the current now is Vs over R1 parallel R2, and the voltage, of course, is also again going to be Vs. We wait for a long time. But what happens just after we close the switch? Just after we close the switch, what happened to the current? Yeah, exactly. The current cannot change. Why not? Well, because it's an inductor. The inductor resists change of current. It's not possible because the voltage would have to be infinite to get a step-in current. Okay, so based on that, we now can confidently say that somehow the current must follow a trace that looks like this. And of course, we know now, based on our experience with first-order differential equation, that this would be an exponential, and we can calculate that, and I'll leave that up to you. What's going to happen to the voltage? Just here, what's happening to the voltage? Does it change? Why not? Well, it's not a capacitor, it's an inductor. Does the inductor say anything about, does the inductor have any problem with the voltage changing abruptly? Has no problem with that. So it could change abruptly. So, but on the other hand, the current is still the same. So the current is the same, but suddenly the resistance here dropped. Well, if I have the same current flowing into a smaller resistor, what's the voltage going to be? Less than before, right? Okay, so the voltage is actually going to decrease here. Okay, so before, in fact, we had the current that's flowing here is Vs over R1, right? That's the current that was just flowing before I closed the switch, and because it's an inductor, it's not going to change instantaneously, so it's still the same. So that's the current, and then what is the resistance? Well, the voltage. If I want to get the voltage V2, I need to, this is my current, I need to multiply this with the resistance. What's the resistance that I'm seeing now? Yeah, exactly. Okay, so that's the value here. Okay, so the voltage actually sags like hell. And then, of course, if I wait for long enough, if I'm patient, it will recover eventually. Now, of course, if my system goes pretty fast, the next clock cycle may be hitting here, and the voltage never recovers even. And maybe then my system doesn't work, right? Okay? So that's really what you're doing when you're connecting your system, your electronic system, to the power supply. Okay? Not good, right? What would you want this to be? How should this look like? Well, it should look like this, right? That's what you want, right? And you certainly don't want any of this. Okay? So I made an example here. I plugged in some values. I used this 500 nanohenries, a 1.5 volt supply. R1 is 1 k ohm, but then R2 is much smaller, 100 ohms. So what really happens is that most of the time we just have 1 k ohm, so 1.5 milliamp flowing. But then whenever the switch is closed, we need a burst of current, about 15 milliamps now, or a little bit more, in order to drive that lower resistance. Okay, and so yes, the current here, the continuous current is only going to be Vs over R1, so that's 1.5 milliamps, right? But here the current that we need when we have both resistors closed is on the order of, what is it, probably 16.5 milliamps, right? Because just into resistor R1, we now need 15 milliamps, and we still have, R2, and we still have resistor R1, okay? So, and again, when we switch, then, of course, the voltage sags, and I can't be quiet over there. So here we ultimately go again to 1.5 volt, but to what value does it sag down? Well, we could easily calculate it, but if I read it off here, we have about 100 millivolts or something like that left. Obviously, I can adjust these resistors to anything. I can go almost to zero. Do you think your system's going to work when the power supply is so choppy, and every once in a while, and every clock tick actually, it's going to go down to just 100 millivolts? It's not going to work, right? So we somehow need to do something about it. We can't tolerate these voltage drops. Yeah. Yeah, exactly. Why a capacitor? Yeah. So maybe the easiest answer would be, hey, you know, a capacitor resists change in voltage. Consequently, here, if I have a change in voltage and I don't want it, I put somebody there who says no way. Right? Okay? So that's what we're going to do. We're going to add a capacitor, and then that capacitor is going to take care of the problem. So here I've added the capacitor. Can you see it? Well, it's here. Okay, so now, of course, there is going to be the wire from the capacitor to our circuit And that wire is going to have inductance, right? But how are we going to make this thing work? It's a very easy way to make it work, but people sometimes forget it, so it's good to think about it. What do we have to do with this capacitor? Yes. Exactly, we have to put it very, very close. Now, if you look up data sheets, and I should have put a copy in here, but anyways, you can look up data sheets, for example, for your 555 timer. Then in the data sheet, it actually tells you there is somehow the 555 timer, and then it has somewhere a VDD connection, and somewhere else it has a ground connection, and in the data sheet, it tells you to put the capacitor here. Why does it tell you to do that? That's exactly why. Well, because the manufacturer, of course, knows that its 555 timer has a very choppy current requirement, and you're going to use wires to connect it, and that's not going to work very well unless there is a capacitor that will be able to supply these chops of current. Where are you going to put that capacitor? Very, very close, right? You have to put it very, very close. You can't put that across the board on the other side of a printed circuit board. You have to put it right next to your 555 timer. How do we get around this problem in the EE40 lab? Patience. Patience. We are very slow. We are building slow stuff. I could easily drive you nuts in the lab, drive you crazy in the lab by telling you, go and do this thing at 100 megahertz. And then you would run big time into these problems. But, you know, at the kilohertz or whatever, things are so slow that we more or less get away with murder. But still here. So we make this one very small, so essentially it's not present. I mean, if you build stuff that goes at a gigahertz, don't just assume that that inductance is zero. It's not, right? But at our speeds, we can make it essentially zero, yes. Really, really close? Well, because then, if it's not close, then we have another inductor here, and that inductor produces exactly the same problem as L1, and so we can put as many capacitors over here. If there is a lot of inductance, the voltage here is still going to do this, right?
So it should be close to R1?
Yes.
Oh, okay. And
Yeah.
then why is it parallel? Can it be just like in series with L1?
Well, what would the actually what happens if let's forget about the inductors for once. What happens if we put the capacitor in series with the power supply? Yeah, it's going to be an open circuit, so that wouldn't work very well. Yeah. Now, if you put it in series with an inductor, then some very interesting stuff is going to happen, but let's not talk about that now, okay? So, that's what you're going to build. We're going to put that capacitor here, and the minute we put that capacitor here, then we have a chance, right? So now, of course, there are some questions we have to ask ourselves. What is an obvious question that we have to ask ourselves? Yeah. Yeah, exactly. How big should we make it? Well, there are lots of ways to do that, and here again, it's I guess we could say, well, we are mathematicians, we solve all the differential equations for this thing. In fact, these differential equations now become second order because you have an inductor and a capacitor. Suddenly you have two reactive elements. We get at least a second order differential equation, a little bit harder to solve and so on. But if we look at this as circuit designers, then we sort of can say, well, you know, that resistor, that switch is closed for some time t. During that time, the current that's flowing, or the flowing is Vs over R2, right? 15 milliamps in our example. So it's flowing for a time t. So the amount of charge that really we are dumping there in every cycle is Vs over R2 times this time t. Okay? That's a rough, approximation. We don't take into account that this Vs actually probably is going to droop a little bit still, even though we don't want it to and so on. But this isn't a totally exact science. Right? We don't need to get this exactly right. We just don't want to be sure that we don't need actually a 1 microfarad capacitor. We put only a nanofarad there, and vice versa. Also, it's not good. Then we put the much bigger capacitor than we would need. And actually, the bigger ones are not as good as the small ones. So then the capacitor that we need is the charge that it needs to supply divided by the change of voltage that we are willing to accept. Right? So we're going to have to accept a little bit of a drop-in voltage, maybe not too terribly much, but a little bit of drop-in voltage. Okay? So that's this term here, 1.5 volts over 100 ohms. That's the 15 milliamps. Then we say that the switch is actually closed for 5 nanoseconds. Well, you need to look at your application. Right? That's just an example. Could be something else. And let's say we are willing to accept a drop of 100 millivolts. Please don't sag more than 100 millivolts, but we accept a little bit. And then we end up with about a nanofarad capacitance. Very often these capacitors don't have to be blazingly large. And actually, I mentioned already sort of in passing before, the really big capacitors, they actually lose much of the advantage of capacitors. Right? The advantage of a capacitor is that it can deliver its charge very, very quickly. Okay? A big capacitor actually can't. If you use this big 100 microfarad electrolytic capacitor, well, it takes a lot of time for the charge to come out. In other words, a big capacitor has an inductor here. Just get it. By making the capacitor big, nobody ever figured out a way to make it that you don't also get an appreciable inductance there. Anyway, so it's actually a good thing to use a small capacitor if you don't need a big one. Okay, so does this actually work? Well, I investigated that with SPICE, so you can see here, put the source, 1.5 volts, put the inductor, here's this R1, here's the capacitor. First, I made it only a picofarad, very, very small. That's way too small, right? Much less than the nanofarad that we figured that we need. Here is the R2, and here, this is our switch. Okay? So now again, here the capacitor is essentially 0. You can't make it quite 0 in SPICE, otherwise it complains. You would have to rip it out, and I didn't want to change schematic. So I made the capacitor very, very small, and what's happening here? Well, it's a little bit hard to read, but what do we have here? So the blue one is VC2, and this is VC1. What are these voltages? Well, here this is VC1, and this is VC2. So VC1 is the voltage across resistor R1, and VC2 is the voltage across resistor R2 on the other side of the switch. Now, of course, when the switch is open, then VC1 should be what? VC2 should be what? Should be 0, right? If the switch is open, if this switch here is open, well, then there is no current flowing through R2, so the voltage should be, VC2 should be 0. Lo and behold, this apparently is when the switch is open, okay? We get that. So now when the switch is closed, then the blue and the green one, they are on top of one another. Well, that makes perfect sense also, because when the switch is closed, of course, VC1 and VC2 are tied together, so their voltages are the same. In between, we see that before our voltage, just before here, VC2 is approximately 1.5 volts, but then the minute we close the switch, VC1 and VC2, they both are going to decrease, and then they slowly recover like this, right? So that's exactly what we expected, right? We don't have a capacitor there. Consequently, the minute we need more current, well, because of the inductor, the supply cannot deliver it. Consequently, the voltage is going to sag. And then, well, if we waited long enough, ultimately this would go back up to 1.5 volts. But, well, very often we can't wait that long, right? Because our circuits, they go at some reasonable speed. Okay? Now, there is something else, and that's VC1. Whenever actually we open whenever we open the switch, VC1 does this. It goes way higher. This is 5.5 volts here. And then it comes down again. It actually goes further down, and then it sort of recovers to about 1.5 volts. What's going on here? Maybe if we look at the circuit, we can better understand what's going on here. Or actually, let's switch back. So just before we open the switch, what is the current flowing through the inductor? What is the current flowing through the inductor when the switch is open and we wait for a very long time? Well, then we just have the resistor R1 that's loading it, loading the supply. The supply is 1.5 volts, we said. Resistance is 1 k ohm. One and a half milliamps, right? So it's just 1.5 milliamps. And then when we close the switch, then we have how many milliamps flowing if you, again, wait for a really long time? What? Much more. It was like 15 or 16 milliamps, right? And then the current's going to be much larger. Okay, we maybe don't wait for quite that long, but the current is going to be larger than 1.5 milliamps, right? Now we suddenly open the switch. What happens? The current here is larger than 1.5 milliamps, right? It's larger than that. We open the switch. Where does the current go? It now goes to R1. It cannot go anywhere else. Well, if the current is more than 1.5 milliamps, exactly, then the voltage drop across R1 has to increase. Okay? And so actually, if this really was the case, if we really built this circuit like this, then maybe the 5.5 volts, depending on what is actually hanging there, is going to destroy our device. And we'll never even be able to see what's going on our oscilloscope. We just plug in new ports, and they break as we plug them in. Okay? So that's what's going on if we don't have a capacitor there, where the capacitor is very, very small. Now we put in the capacitor of 0.5 nanofarad, as we calculated that we need about, and again the blue one is the voltage across R2. So that's going to be 0, and then it's going to go up to about 1.5 volts, and then it's going to go down again when the switch is open, and so on. And the voltage VC1, well, it's just going to go up and down a little bit, right? We calculated, we designed it for about 100 millivolts, a little bit less or so. So it's going to have a little bit of ripple, this is called, but it's not going to sag down to 100 millivolts, and it's also not going to shoot up to 5 volts or something like that. Okay? What else would you like to know if you designed this thing? Yeah, exactly. Hey, you know, now what's the current? Well, shown here in green is the current through the inductor. What would you expect the current through the inductor look like about? About constant, right? It should be about constant, because inductors really don't like it when the current's changing. So consequently, if the circuit is operating right, well, probably the inductor current is going to be about the same all the time. What do we expect the value of the inductor current to be? Is it going to be 1.5 milliamps? Yeah, it has to be somewhere halfway, right? During half of the cycle, we need about 16 milliamps. During the other half of the cycle, we need only 1.5, right? So in order to deliver the amount of power that we actually need, the current needs to be somewhere in the middle. And what is it here? Well, it's about 9 milliamps. Okay? And it doesn't change a whole lot. Okay? So the current through R2, R2, What is that current going to be? Well, it's going to be 0 when the switch is open, and it's going to be approximately 15 milliamps when the switch is closed, right? Okay, that makes perfect sense too. Well, you designed this right. What's the current IR1, incidentally? What's the current IR? I would like if somebody who is sleeping now who can try to wake up and figure that out. It's going to be a lot harder when you're sitting at your desk at home to figure that out. Okay? So what is the current IR1? That's very easy. Yeah. Well, no, somebody else. Hey, you know that there ought to be somebody else who. Yes. Thank you. 9 minus 15. I'm not quite following.
Like the current going in, and then you have the current in branch, and it's balanced to 0.
Okay, that's. Well, but there is also the capacitor. There is current flowing in the capacitor. We didn't look at that yet. But what's the voltage across here, across the resistor? Yeah, it's the same. But hey, you know, the whole point was to design this voltage to have a particular value, namely. Yeah, this should be 1.5 volts, right? That was the whole point of all our argument was just how can we make the supply to our actual devices, which are 1 and R2, how can we make that voltage actually be equal to the supply voltage, 1.5 volts, right? Now, granted, there is going to be a little bit ripple and so on, so we may be 100 millivolts off or so, but roughly, the voltage across R2 is going to be 1.5 volts. In fact, no, here. In fact, that's what we found from simulation, that it actually did work. Now we are just figuring out what's going on with the currents. So the voltage across R2 is approximately 1.5 volts because our circuit now works, because that capacitor keeps the voltage constant, and consequently the current through R2 is now not hard anymore. I don't know. You'll figure it out. Here, 1.5 milliamps, right? Approximately. And that's exactly what you get here. It's this blue line here. So now I'm out of color, so I have to use the yellow one, but at least... so I see one. The current that's flowing in the capacitor. What would you expect that current to be? What would you expect the current in the capacitor to be? Is it going to be constant? Is it going to be constant? Yeah, it has to, right? It has to somehow go up and down. While when the switch is open, what do we expect that current to be? Actually, now your argument with the difference, now that difference is exactly the right answer here. Anybody. I wish that there were 80 people or so who could tell me the answer. Because afterwards you're going to come and ask me. So what is going to be? Here we know we have 1.5 milliamp flowing. We know in the inductor the current is, it's greater than, that was, the inductor current was on the order of 9 milliamps, right? With the large capacitor, right? The greater than 1.5, that was during the small capacitor case. And there we have 9 milliamps flowing. Down through R1, we have 1.5 milliamps flowing. So the current into the capacitor when the switch is open has to be 9 milliamps minus Minus what? Okay, I'll let you figure that out. Huh? Yeah, you know, and I know, and you know, and so on. I would like that somebody else tries to know too. Okay, it's getting a little bit harder, so you'll need to sort of put up with that. We have more than resistors now. So the current, when the switch is open, it's going to flow, a lot of current is going to flow into the capacitor. Now, when the switch is closed, what's going to happen? Well, then here, what's the current here? About 15 milliamps, right? And so then suddenly a lot of current's flowing that way. And that's exactly what SPICE tells us. The current IC2 is, while the switch is open, and there's a lot of positive current going into the capacitor because the capacitor is being charged. And then, when the switch is closed, well, then the capacitor actually delivers current to where? To R2, right? So the current is negative in the capacitor because it's coming out. It acts like a source now. Okay? And then, of course, the whole thing repeats. Okay? So the choppy current, of course, is still flowing. Sometimes we need very little, and sometimes we need much more current. But that choppy current is not flowing through the inductor. The current through the inductor is almost constant. It doesn't change a whole lot. Okay? Current through the inductor is almost constant, just enough to supply all the power that's needed by the circuit. Because, of course, the capacitor cannot somehow create that power or so. But the capacitor can take off these peaks and fill in and absorb the valleys, right? So the capacitor is actually supplying the choppy current. Okay? And the capacitor, we put it very, very close, so we don't have yet another inductor to deal with. All right. Any questions? Okay. Please look at this. I do not have many slides with a red frame around it, so it means something, the red frame. Make sure that you understand this. Look at this. You need to remember also the equations for the capacitors and the inductors, the differential equations, there are just two of them. But more important than these equations is this stuff, right? How does it actually behave, right? What do we do if we were an inductor, right? We don't want the current to change, for example. And then go through this example again and make sure that the questions that I asked you, that you can answer them. And if you can't, come and ask questions. Okay? Good luck. Thank you.